Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about new developments in ICE engine, which seems odd in 2025, but let's dive deep into it. So why do we need development in internal combustion engine? Well, reality is EV is not fully cooked, meaning that technology was rushed into the market because of Elon Musk, and basically, practically speaking, that puppy is 3 months old rather than 9 months old. So it's not there. And here's the deal. You can see it in oil charts, as in global oil consumption by any major nation. Outcome is zero, as in it has zero impact. The biggest impact we had in oil consumption was pandemic. Pandemic actually dipped it. Nothing else had it. And again, you might look, okay, it's not old enough. No, it is old, as in old as iPhone. That's the same time EV happened. And be mindful, there were other companies that were doing EV before Tesla made it popular for some reason. But people were working on it. So reality is, as of now, best analytical data, like actual real world data, suggests is that best you are getting out of EV is this line. Instead of going shui, it is going like this, and which again I find rather useless, simply because world's population is not expanding, and not to mention more countries are going into recession rather than swimming in money. So it's like people's living standard is going up. It's like, which country? Like, genuinely, I'm genuinely curious. So from 2010 to 2025, things are not looking up. Population is declining. People's living standard, inflation are running away. So who the heck is drinking all the oil? Reality is EV is not real. Like, impact point. It's almost like you released a vaccine for pandemic and pandemic still going on. So fundamentally, it's not real. Let that figure. Factually, data-wise, look into Europe, look into Middle East, look into Africa, look into North America, Asia Pacific. Heck, even China. People are like, China has EV. No. They have graveyard of EV. They don't have EV. Look into their oil consumption. It's shoo. And again, their population has shrinked before, right before our eyes. They were the most populated country. Now India is. So don't say the population one. Now, here's the deal. Let's just assume you have magical wand, right? You are some politician who smokes weed, and you're like, okay, what if I just forced everybody to do EV, like how European Union is thinking, is like, we're gonna ban combustion engine because let's F the public. Or what if you really do not study mathematics or chemistry or any sort of round trip efficiency or thermodynamic conversion efficiency, or how 8 megajoule is less than 32 megajoule, hydrogen. Here's the our grid worldwide cannot do that. Like, for example, take all the oil consumption, take the lightest fuel, let's say petrol, how much petrol we are burning, convert that into kilowatt hour, divide that by like 30%, the conversion, or 25%, go yellow on it. That number is so huge that our global electrical grid will collapse the moment you put that much load. Kaput, instantaneously. It does not matter one place or another, all of them. Like, this is the world energy grid growing from 1990 to 2024. It has went from 10,000 terawatt hours to slowly reaching 30,000 terawatt hour. That's nothing. Oil is like, bruh, that's nothing. So flat out right now, you cannot do EV conversion. And if you cannot do EV conversion, you cannot do hydrogen conversion, because hydrogen has poor round trip efficiency. EV can give you, give or take, let's say 90% is easy. Like a good built system, 90%, as in 100 unit you took, 90 units will go into your electric motor. Hydrogen, you took 100 at best. Like, I am being optimistic AF, 40 will go to your wheels, meaning twice the price, meaning you will burn your country. And what about the energy grid transition? It's going good, but again, you will find something weird. Like, people talk about solar, like going solar YOLO on it, but why the heck wind share is so huge? And again, compare this from 1965 to now. It's like, why is that? Well, wind energy has this unique advantage that whenever a single plant is built, it's huge. Like, they started talking, it's like 2 gigawatt, 22 gigawatt. Heck, one turbines are now reaching above 10 megawatt. Like, most new wind farm that is being built, it's above 10 megawatt right now. As in, you can easily go into, I think, Halide X or something like that from General Electric. Those puppies are 16 megawatt, 1.6. That is damn high. And you put them on offshore where yield time is very high. So it's going, like, the amount of energy that is being created by wind is huge. And then solar is also going huge. And then we have some minor things here and there. So realistically, at this point in time, our grid needs time to grow for managing EV. It's not ready yet. Let that be very clear. Absolutely. Going into full EV will shift delete your country. Flat out. Do not give me comparison to some teeny tiny weeny whiny nation. Give me comparison in top 10 population. All of them will have the same outcome. If you do that much EV conversion, instantaneously electrical grid will go kaput. So that is there. So what does this mean? Well, grid needs time to grow. Will grid grow? Of course it will grow. You can see it's been growing slowly, but it is growing. So it will grow. That's a sorted problem. No, you do not have to worry about it. But you cannot rush it. Meaning, where will you get the money? Where will you get the money to force people to jump into EV and then at least 5-10x the money to create the grid infrastructure to handle it, and then 20 to 40x amount of energy production to handle it? Yeah, it's not happening anytime soon. It has to be done slowly. It has to be grown, like how you grow a tree. So it cannot be done, you cannot rush it. That's not an option. So what does this mean for you and I? Simply means ICE engine, bare minimum, it has 50 years and easily 100 years left. Like, if I'm being very idiotically optimistic, let's just say somebody invents something super magical, or heck, we crack fusion energy. Only then I can see there's only 50 years happening, but likelihood is almost zero. Like, I'm too old for fusion now. But 100 years, like, easy. You do not have to worry about it. And what does this mean from a population point of view, from pollution point of view, Earth's environment point of view? If you can save 10% fleet-wide, it will have such a ginormous impact on CO2 emission. It will show up in satellite. Like, that's how we know how big of our pollution footprint is. When pandemic slowed some of it, it's just like satellites were like, whoa, Earth is clean. What the hell? All the remote sensors are like, bro, what the hell? It's like, that's how we know. And that much impact will happen if you can give only 10% to all combustion engine. And you're like, okay, what about future, right? Future, the only viable solution that we have, which has the least amount of consequences, the most amount of viability, is seaweed biofuel. Nothing else has the probability of working. You cannot grow it on land. You cannot grow ethanol or anything on land simply because you will shift delete food crops. And penalty of that would be stupendously high food prices. Indians are slowly starting to realize that, because our politicians smoked ethanol. So that's the reality of it. You can only grow in sea. And what about bioenvironment? Here's the deal. You do nothing, whole planet dies. You shift delete a small area in sea. And again, given the surface area requirement, it is super easy to do. And in India's point of view, again, I'm not talking about Afghanistan, I'm talking about India. India's point of view, we will not even touch international water. Like, we can literally take care of in our own economic zone. We do not have to go to China or other places. In that only, we can easily take care of it. So saving planet takes priority, then you have to make sure in combustion engine is better. Right now, I'm talking 2025, fundamentally. So you can negate all the CO2 talk of like EV simply by improving combustion engines by 10%. That's the reality. Like, check all the data, all your sources, go YOLO, especially on crude oil. There are 10,000 data sources on that, go YOLO. So what exactly is the problem? Well, problem is internal combustion engine is very complex beauty. Like, it is brutal as in terms of power and precision. And again, because I'm working on making one of them, I'm realizing like it is brutal. You will think, oh, I have the CNC machine, I'm going to put this and come out, the part does not work. It does not match the tolerance requirement. Like, because we have mass produced it and we have fine tuned the whole design, it feels like it's an engine block. No, it's a black magic. Fundamentally, like, it is complex AF. And power and precision, like, think about this, like, we are talking about something that handles a boom event 6,000 times a minute. Is like boom, a boom, a boom, and you can have like 12 of them or 16 of them in a car. It's like, what? So fundamentally, there is a lot of complexity, and penalty of that, there is a lot of issue at the core level. Basically, the core things we use in an engine, they have some problems, and then there are certain physics level things that make things complicated. So can we change it? Can we solve it? Of course. Exactly how we have improved from what basically Henry Ford had. Like, basically, if you take my cheap car engine, as in like a Maruti Espresso K10 engine, you gave that to basically Henry Ford, he will have a stroke. It's like, what black magic is this? And that is the cheapest engine you can get. So fundamentally, innovation will allow you to make it even better. Now, why people are innovating now, not 70 years ago? Petrol was cheap. Nobody was caring. It was cheap. Like, I know the fuel prices when I was in school, and I'm only 33 years old, 33 or 32. That time fuel price was 40 rupees per liter. Now it's 100. So price has almost more than doubled in less than, like, what will I say, 30 years, so to say. No, why I'm saying 30, 20 years. So again, as fuel becomes more expensive, more, then you will start to notice, oh, my pocket is starting to hurt. Like, rich people do not worry about mileage. That's why you do not see what is the mileage of Bugatti Veyron or what is the mileage of Ferrari. That does not make sense. Like, if you're driving a Ferrari, you are not poor enough to worry about those things. You are rich enough where it's like, just go to can, fill it, go home. I ain't got time to count. So That is there. Innovation can make things a lot much better. Now, why we have such a cumbersome rule with a combustion engine? Well, simply because it's hard to burn fuel and not have NOx emissions. As in, this law of physics says hotter your boom event, the more useful energy you can get out of it, like Carnot efficiency. Now, here's the core sink is fixed. Like you are in India, that is 60 degrees Celsius. Cool, awesome, done. So what about hotness? Well, if you can burn at 800 degrees Celsius, that's good. What if you can burn at 1500 degrees Celsius? Ultra good. So you can have huge efficiency gains if you go from 800 to 1500 degrees Celsius. But here's the deal, because when you are flowing air into the engine, it's not oxygen only. You have a lot of other stuff. The biggest other stuff is nitrogen. And if you have that much nitrogen going in there and the temperature is that brutally high and you have some oxygen, it will create NOx. So basically, the moment you start to reach 1500 degrees Celsius, NOx emissions starts to go up. But again, physics wants you to be higher temperature. Physics is like, bro, you want efficiency, you have to have higher temperature. But if you have higher temperature, like diesel engines, you have higher NOx pollution. That's why people hate diesel. It's like diesel loves compression ratio. People started to make high compression. It became thermodynamically more efficient. So people loved it. People used it more because again, it was actually consuming less fuel. But while the CO2 output went down, the NOx output went YOLO. Like right now, it is so bad that we have to use ammonia in exhaust gas treatment to make sure that it does not pollute the whole environment. Because again, physics is like, bro, heat it up. And NOx is like, easy, bro, easy. So, and again, same applies with jet engines also. They're like, we want fire. And NOx is like, are you sure about that? So you can see like how we have two things that are firing missiles at each other. It is hard to manage. And RPM, that's another vector you are familiar with. RPM is so weird, as in like, the lower you make it, the more efficient it becomes. Right now, the most thermodynamic efficient engine is basically marine engines that are used to propel ships. Those puppy can touch BSFC value of as low as 160 to 150. That is magnificent. That is almost touching 50% thermodynamic efficiency. But here, or some designs are 31, and by the way, if you have that turbo energy recovery, it goes even higher than that. That is magnificent. So why not all our engines are that good? Well, those are low RPM. How low? 100, 150, they are low and slow, meaning they do not have that much parasitic losses. And compare that to your car engine. Yeah, your car engine can start at 3000 and it will go up to like, 4000 or 5000 or some like high performance 12,000 RPM. It's like, that's the brutal part of it. The higher the RPM, the higher the density. Cool, awesome, GG. But poor the basically mileage, so to say. So if you're like, okay, why not just make a big engines, like let's say a locomotive. If you make a locomotive engine as huge or like, as low RPM as what is used in ship, it will not fit in a train. Like the whole train will not be able to fit it. It will be so big. So that's the fundamental issue. That's why they are only works in a container ship. That area has the space, weight, constraint, loose enough where they can actually do that. So you see, there is a paradox. Like you're like, okay, what if I want more efficient because petrol is expensive? Cool, awesome, reduce the RPM, but your engine size grows. You see the paradox? So this is the issue. Another aspect is, what about compression? What if you like go it? Like if we started with very low, like 4:1, 8:1. Now you're like 14:1. But here's the, you can't really go that high unless you have like octane, something like ethanol blend into your fuel, because again, knock will happen. As in, before you reach your top dead center, your fuel and air mixture will auto detonate. It will kaput your engine, like flat out kaput your engine. So even though physics says higher the compression, higher the temperature, higher the efficiency, knock says, are you sure about that? So there is some genuine problem. Like it is not easy to design an engine that is like super efficient and not polluting, super efficient and small. So you can see it's a very brutal, and it's very not black and white, because you're like, okay, what if the engine is bigger? Yeah, the engine will weight so much that your per kilometer mileage goes down. So fundamentally, it's a messy problem to solve. So what can we do? Well, there are a lot of options. So option number one is hybrid, because here's the, right now road engines have very tough life, meaning you can easily find road engines that have this sort of stupid curve, as in they're supposed to work at low as 500 RPM and as high as 6500 RPM. That is huge. Like to give you a context, your power plant generator rotates at 1 RPM, the end. It starts, it rotates, the end. There is nothing more than, and it runs your whole civilization. It's like, bro, if it's a 50 hertz system, 1500 RPM, it's a 4-pole generator, or it could be 2 poles, so it's like 3000 RPM, done, go home. It stays there. It's like 3000, the end. There is nothing after that. Combustion engine, we starting traffic and all that. It's like, this is brutal. Like, your engine does not like this. And you can see that in BSFC chart. Let that be very clear. Every engine is measured by that. You can measure the mileage, as in like kilometer per liter or miles per gallon, based on the vehicle. But engine cannot be measured that way. So we invented BSFC. Now BSFC is calculated by, like, you set the engine to a fixed RPM, you calculate the RPM, and then you put load on it, variable load, as in like 10 Newton meter, 20 Newton meter, 30 Newton meter, 14, 50, 60, 70, 80, 90. And you do this throughout the RPM range. And that's how you get the BSFC curve. Now this tells you where is the sweet spot. Now, because again, combustion engine is so complex, so weird, it has this weird tendency. If you're like, hey, what if I idle it? You will burn more fuel. Like, it is better for you to shut off your engine than to idle your engine. Why? For example, let's say you're 2500 RPM, cool, normal, city traffic, and you're just idling your engine. Your torque load goes down. Here's the deal, you will burn as high as like 500 grams per unit of energy. Like, only 1 unit of electrical, and again, you have enough parasitics that you do need load on it. So 500 grams will be burnt just to make 1 unit of electricity. But what if you put load? What if you put 70 Newton meter? Like, you're like sweet spot, you're loading that puppy. Now you only need 225 grams of fuel to make 1 unit of electricity. That's the key point. So right now, because we want engines to work in such a vast range, we cannot utilize this sweet spot. We want our engine to stay here. The end. Why? Petrol is expensive. The end. Do not talk about anything other. We want power. No, you want mileage. You can't afford power. Otherwise, you will buy Bugatti Veyron. So flat out, we want to stay there, and we cannot afford to. Environment cannot afford to. Our pockets cannot afford to. So we want that. So we have created a lot of technology to extend that band, so to say. We have variable valve timing. Almost all engines have variable valve timing. Some supercars started to introduce this idea, which is slowly trickling down. Cylinder deactivation. What if you have, like, 6-cylinder engine, you turn off 2 of them when you are idling, because again, you do want some load. It's better to have dead cylinders rather than, like, all cylinders working at partial load. So we do everything. But here's the deal. Current engines right now that is available in market, that is in your car, it's very efficient, like bonkersly efficient. If you have a real-time mileage counter in your car, you will notice that sometimes the numbers are too good. Like, it's too good. It's not too good. It's when it stays here. So here's the deal. But because of variable load, your engine never stays at the sweet spot. It goes like this. That's what happens to your engine. That's why it's not shining. Because again, you give accelerator, your engine computer is like, okay, well, how much load I have, how much torque is that, feedback is happening from the transmission. And again, even if you are in here like perfectly well, then the wind starts to flow, your Newton meter will go up, your efficiency will drop. So fundamentally, this is the outcome. You can check this in your OBD port. If you have an OBD data logger, you will find the fuel mapping and a lot of other things. So you can backtrack what is happening. It's brutal. Like, it's brutal. Your engine wants to stay at the sweet spot, so it gives you magical mileage, but you cannot stay there because again, the engine is not floating. It has variable load. So series hybrid solves this problem specifically with battery storage, because company figured out that at least half of the problem can be solved, as in, like, you can lock the RPM if it's a series hybrid. That's how you do diesel locomotive for 1 century. That's how you do, and again, diesel submarines are even better because again, they lock the torque also. So they get the best mileage conversion. So why don't we do with car? Again, petrol was not expensive enough. Now, at development of EV did allow this technology to be viable. Meaning, right now you can have a series hybrid, as in you have a combustion engine that is driving a generator powering a battery powering the motors, because motor can handle these things, random efficiency, and motor's efficiency does not change that much unless RPM goes way too low, way too high. It's like, it's good. It has much wider efficiency curve, and if you have good enough motor driver electronics, it's like negligible. Like, you do not have to worry. It will be like, okay, I'm going to consume this much unit of energy to run 15 minutes. It will take that much. So that way, and again, battery allows you to have a reserve. Basically, this puppy stays there, gives a pipe. That pipe would be, let's say, 100 kilowatt. That pipe is 100 kilowatt. Your buffer handles it. Buffer is like, slowly fills up, slowly drains, fills and drains. When you're like, okay, I need to take over, the buffer drains, not the engine. Engine does not change the loading. Engine stays at the sweet spot. The battery goes down. Then you do regen. Battery absorbs the energy. Generator does not shut off. So it turns on, stays on the, charges the battery, turns off, the end. So how much of an impact this will have? Well, if you start to do this on large puppy, well, 30% gain is viable. Like, it is like, yeah, you can do that. Especially if you have both, let the RPM and torque loading, both has to be locked. And 30% on a big vehicle, that is like you are yeeting one car out of road. That's how magnificent impact would be. and no new technology required. Everything that is needed for this is right now in market in 2025. And Toyota had this puppy in 1993, I think. That was the first time they started. They had this technology with nickel halide battery, but people smoked too much Elon Musk. They're like, no, we want 100% EV. It's like, bro, grid is not ready. If you had given this, everybody would have EV by now. Everybody would claim like, oh, I want 10,000 kilometer range. No, you don't. You say that, but most of the time you can't drive that much. Just have a small range, charge your battery, and if you forget to charge it, your combustion engine takes care of you. And again, Toyota was halfway there. They almost reached it, but they were like, what if we had series parallel hybrid? It's like, no. But to be fair, that time I think AC compressors were not electrified yet. Right now we have AC compressors that are electrified. So that problem is solvable, and you can take care of big loads today. And if you have electrical infrastructure growing, like, let's say a lot of trucks are going, then people can like, hey, I can put a high power charging station because I have demand. Then they're going to put there and charge the battery directly, plug in hybrid. So hybrid will give you direct pollution reduction right now. If you go full EV, all you are doing is pushing the pollution somewhere else. But hybrid will actually reduce pollution now. And if you did for almost every combustion car, 80% of people would have EV. 80%. And 20% of the time they're like, oh, I'm actually driving long distance, so I'm using combustion. And again, even that, the combustion will be far more efficient. Sweet spot. But no, everybody wants full EV. Now, okay, that solves the how can you get the most out of the engine you have. But what if your engine became better? Well, there are a lot of refinement possible in ICE. Let that be very clear. Even though it looks like a 150-year-old technology, it is 150-year-old. There's a lot of things that can be done. For example, there are a lot of people working on removing the puppet valve. The valve that you goes in and out, that physics does not like it. The valve is like this. Air has to come like this, go around it, come here. Physics is like, nah. So some people are like, what if you have rotary valve? Now, does it work? Yes. Then why don't we use it? Well, it has a problem with sealing. Basically, when we go ba-boom, the seal does not hold up that well. Puppet valve is GG when it comes to seal. It's like, you can go kaput in there. And it's like, I got this. Not a single atom of gas will leak. It's like that good. When valve is, it leaks too much. So people are trying to make that work, and let them figure patents expire in 20 years. So if you see, oh, somebody else has already patented, you can still make it, especially after 20 years. So as in like from patent date. And some people are trying to bring a two-stroke back. Why? Two-stroke has one advantage. It solves the energy density issue, meaning your engine becomes compact, as in less mass. So it becomes more efficient, more logical for range extender. So these people are making this engine. I have linked the video down below. And it's really smart. It's basically what container ships are doing right now. So it does come with one penalty, that they have to use supercharger. Supercharger directly runs on the crank. It has a higher phantom drain compared to turbo. Turbo works on exhaust gases. So turbo does not have the load. That's why we are switching to turbo, not supercharger. But again, then why they have supercharger? Because this engine cannot breathe. It does not have the ability to breathe. So you have to force air it. You have to it. But it does work. And again, they solved the rotary valve problem by making sure the boom event happens in an enclosed environment. You get the full oomph, and by the time you have to exhaust it, that time is like, hey, even if this leaks, it's like, yeah, you're supposed to let gases go. Is there. And again, it does not use the second part of the chamber to suck air in. That's the biggest issue of two-stroke engine. Thankfully, I can do the same thing with a CV engine. I'm asking Ron to design it because again, we have linear travel. We can have the backside of the piston acting as a compressor. So we can breathe without supercharger or turbocharger. And this, I think, if I had direct talk with them, yeet the supercharger, put a turbocharger there with basically the same turbocharger that is utilized in F1, basically with thermal energy recovery system. Why? At the starting motor, when this has to breathe, you start it and the electric motor spins the turbo. So this can actually start. Once it starts, exhaust gas will keep it running. And then you can extract that energy also, because again, turbos are what we call positive feedback loop, meaning you keep it running without any what you call retardation of it. It will go YOLO and it will boom your system. So you put load on it. That's how F1 can achieve 51% thermodynamic efficiency. And large container ship engine, again, they have turbo and they can extract upwards of 500 kilowatt of electrical energy. So much electrical energy that they can shut off auxiliary generator. The propulsion engine and aux generator is off. It's like, bro, we do not have to burn it. Turbo has that much power. So that's how I will improve it. And yeah, it will make it electrically a bit more complex. But again, everybody wants BSFC. This BFC is good, but not that great. I think 230 they have, 230G. So not that great. But again, that will solve the problem. They can easily make it even better. So a lot of people are working like how to make a two-stroke that does not burn oil in a small scale. Ships one already do that in small scale. and then few are making wankery rotor engines, like this sort of engines, and a lot of people are working on removing the crankshaft, like CV engine, my design, and not my design, Ron built it, like my company. And then you have a Wasi engine that is having a disc that is spinning. Then you have a Scotch yoke engine that is going to Scotch yoke design. Lot of people. Why? Well, crankshaft is the biggest physical limitation. It's like this motion going bam, 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 burns a lot of energy away. If you can convert that into rotation, as in like linear to rotation without wasting energy, you should have bonkersly high BSFC, as in like free piston engines, in principle, if they really work that good as people are claiming, should touch almost 130 G. Be mindful, right now world record is 150. So a lot of people are working on changing engines, and again, this engine is really good. And again, with my with CV engines linear design, we can literally remove the turbocharger or have turbo to extra oomph. So that is doable. And again, if you're like, okay, what are the three differences into this? CV engine has all rolling elements, and Wasi engine has sliding elements, and Scotch yoke has sliding element. That's the core difference. So a lot of new engines are being worked on right now, including that one weird one-stroke engine, which again is a two-stroke engine. Marketing term one-stroke, it's two-stroke. But a lot of people are working on it right now. So what can we expect in the future? Well, reality is EV is not ready. Let that be very clear. You have to actually accept the factual reality. EV is not ready, and our grid is definitely not ready. It's like, bro, not even there. So range extender give us time to expand, meaning you have something like this, which again, people were smart enough to do that in lead acid battery era. So we should have done that. Like basically imagine a world where Toyota, instead of making series hybrid, they were just making series hybrid. Instead of basically nickel halide batteries, they had lithium ion. We could have been like done, sorted, go home, like just go home. Everybody has electric, and when they have combustion, they have very high efficiency combustion. That will literally have a ginormous impact on the planet, especially on light fuel oils. I think it would have like day and night. Again, you can see that, like this is dozer from CAT, D6EX, I think they call it. D6XE, next generation electric drive, how they're doing. And again, this is same done in dump truck, where they have combustion engine driving a generator powering a VFD, or in this scenario, I think it's complex enough to have VVFD, variable voltage and variable frequency, driving the traction motors. Why you want to do that? Again, that allows you to lock the RPM at sweet spot. Torque does go up and down, but it is much easier to compensate an engine for torque changing rather than the whole RPM going YOLO, because again, RPM changes the time variable. So fundamentally, people are doing that, and it's like, hey, it saves fuel. You would say it has so much conversion. No, it saves fuel. Why? It's sweet spot. So we can save planet today. At least give us enough time to have better technology to clean everything better. But this whole obsession with just having electric only, and again, you can see the BYD, they started with electric only. Now they're like, yeah, that was stupid and cocaine. Now we are hybrid also. Series hybrid solves all the problem, or if you want technical term, range extender. So right now, flat out, lot of life is left in ICE engine. Never worry about it. Or no, like why people are working on it. More than enough life is left. Like, do not worry about it. And global economy cannot afford full EV. Like, we are nowhere near where you can bankrupt enough people to justify full EV switch. European Union can smoke it. It's like by 2050 we're gonna ban it. Yeah, you're gonna shift delete your country if you do that. So good luck. So right now there's a lot of hope. Again, I want EV to happen, but again, you have to put EV with training wheels. It's like, bro, you good. Make the battery. Like this is the battery's cell capacity theoretical. This is where we are right now. You need time to go here. Training wheel for that time. And again, do not have huge batteries. Have small batteries that can be swapped out. Have a combustion engine to safeguard it. As in like, do not let it go above 100% charge. Do not let it go below 10% state of charge. So combustion engine like, yo, got it. And again, you do want your combustion engine running once in a while to handle it. So there are a lot of options. And combustion engine is still here. It's gonna be here for a while, for a long while. So this was my presentation on basically why a lot of interest is being done on combustion engine in 2025. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.